It's so nice to be able to speak in a real audience. It's been a while since I have done that. And so thanks for everyone who came here and also the audience that's online. So I was asked to talk about my research, and I decided to talk about some of the work we are doing on toxic pollutants in the environment. And many of you are aware of some of these chemicals that are out there in the environment, especially in the water. And the ones that I focus on in my work are these pollutants that come from past discharges. We banned them many years ago. Some of these chemicals were banned 50 years ago, but they're still out there in the rivers, and they go up in the food web into the fish, which some of us may like to eat, or the wildlife might get exposed to these chemicals. And in the bigger picture, this is an issue of externalities that didn't get internalized in our practices back then. And somewhat similar to what we are facing today with the issue with global climate change. The externality with carbon emissions are being passed on to future generations. And in this case, this is our previous generation in the 50s and 60s when we saw the heydays of industrial activity in this country and many of the other industrial countries. We ended up releasing some of these chemicals, which became an externality at that time that we are having to try to deal with today. So they continue to pollute our rivers, major ecological damage, and also potential human health impacts from exposure to these chemicals. We can measure some of these chemicals in human blood, human breast milk, and figure out the risk that's being caused to the population. And there are many fish consumption advisories, for example, in the waters in Maryland, and coming from some of these bioaccumulative pollutants that we have released in the past. And you see the picture on the right in your screen there of the advisories in Maryland. Some of these rivers, many of these rivers have these advisories with colors coded red, where the fish you are not supposed to eat because they have too high a load of these pollutants that came from the past. They're not being released today. So in my research, I look at what these pollutants are, how they are still getting into the fish. And once we understand these pathways of exposure, we can start thinking about interventions. And that's where our engineering comes in. But the science comes first in terms of understanding who they are, how they are behaving in the environment, and what we can do about solving the problem. So the last one we do is how to reduce the impact from these pollutants. So one of the things managers do for sites that are contaminated is put out signs like the ones that you see here. They're effective to some extent for people who would read those signs and act accordingly. But then you see right behind those signs, these signs were actually in this river, which is in the western part of Baltimore, and you see kids catching fish. And there's a lot of people who would catch the fish and eat them. And the impacts are much greater on underprivileged communities where they may not be aware of these advisories, or they have to catch the fish to bring it to the table. So there is a huge impact in terms of who the impacts are being imposed on. And then beyond the human impact, there are these other impacts where we have this bird. This is a fish-eating bird. I took this picture in Virginia Beach earlier this year. And of course, there is a pop quiz now for you. So who can identify the bird here? There we go. Wonderful. There is bonus points for identifying the fish. So who can identify the fish? So it started off as a bird watching trip for me and ended up being a fish watching trip because this osprey, there were a bunch of ospreys that were breeding, and so they were bringing this fish back from the ocean into the nest, and I saw a glimpse of the diversity out there in the waters. So this one is American shad. It's an anadromous fish. It lives in the Atlantic Ocean, but comes up through the Chesapeake Bay into our waters to spawn. And an interesting fact is that it comes back to the same river where it was born. It's quite amazing they do that. As they come up in these rivers, in the coastal waters, they get exposed to these pollutants. which they then pass on to whoever is eating them, including these fish-eating birds. So the heydays of when these chemicals were released, and these are classes, the class of chemicals that bioaccumulate in the fish are things like pesticides, like DDT, a range of flame retardants, and the impacts are seen more heavily on the top predators of the system. That's where they bioaccumulate a lot. And we nearly wiped out the population of some of these birds, like the bald eagle and the ospreys in this country. And it's made a big comeback because we clamped down on the releases of these chemicals. So we study these chemicals. So one of those chemicals that we study are called polychlorinated biphenyls. And these are flame retardants. They had great chemical properties. It would make an oil not catch fire, which was great. It was used heavily in transformers and capacitors where you need an oil to act as a heat transfer fluid. But you can imagine when that transformer is not acting quite right, or you draw too much power through it, it heats up, and that can cause an oil fire. So Monsanto came up with this wonderful chemical that you could add to that oil and not let it catch fire. But it's left its legacy. We're not able to internalize or even conceptualize the cost of this chemical in terms of the damage it would cause to the environment later, which we're trying to deal with now. For example, General Electric spent nearly $2 billion cleaning up parts of the Hudson River, and they're not done yet. And that's the cost that's being borne by the industry and sometimes the federal government and us through our taxes today. So that's how some of these externalities get passed on to the next generation. So we, as part of our research, we start with understanding the problem. So I explain it to my students. The first thing and the most important thing you need to do is to be able to define the problem right. So we spend a lot of time doing that first. To be able to do that, we have to understand the science behind it. And you can imagine when you're talking about these chemicals going up the food web into the osprey, there are a lot of these steps involved. There are chemical steps involved in terms of what you see on the right, on the left of the screen there, of how these chemicals that are now buried in the mud is slowly making its way into the water, into the little organisms, the plankton and the algae and the little fish, and how it goes into the big fish and into the osprey or the human who catches and eats that fish. But it's a measurable quantity, a measurable process if we do the right measurements. So a lot of our work goes into doing the measurements right so we can define the problem. And then the next step is in defining the problem is being able to understand not only the direction of these arrows, but quantifying those arrows. And then linking that with human exposure and risk. And once we get that picture right, we can bring in the intervention and cleaning up. So here are some pictures of some of the work we do. This is in the Anacostia River, supported by Washington, D.C. government, trying to understand the problem in the Anacostia River, which is polluted. D.C. wants to clean it up and make it fishable and swimmable. Before we can do that, we have to get rid of the pollutants that are in the river, figure out where it's coming from, and then address those sources. So our students are working, we have been working there for nearly 4 years now, and we are trying to define the problem right. We are doing measurements in the water, measurements in the fish, measurements in the air phase, and building up these models that describe how these chemicals are moving around in that system. So as I said, building these models, one of the key things we do, once we do these measurements and understand what these chemicals are, what concentrations they are in different phases, we then have to describe it mathematically. So in the work we do in engineering, we have to understand the science well enough that we can describe it quantitatively through math. And once we are able to do that, we can do projections, we can simulate interventions, and we can choose the intervention that will give us the best outcome in terms of reducing risk either to the human population or to the osprey, whatever is being impacted. So that's what we do. We do these measurements, we link it up with models. Our models are physical models of how water moves, how chemicals move, and also biological models of how organisms behave. Who eats who is the big question in trying to understand, for example, in the food web, how does it go up into the American shad? And then once we get that picture right, we think about how do we manage these types of sites. So the picture you see on the right here is me with students sampling in one of our sites in, this is Fort Eustis, Virginia, where we have a beautiful wetland teeming with wildlife, but it's contaminated with that chemical, polychlorinated biphenyls. So we did a set of measurements, we figured out what's causing the problem, we came up with solutions in the lab, and then we are transitioning some of those technologies out into the practice. So in the next slide, I'll show, we started off with looking at understanding how these chemicals which are buried in the mud from the past releases are getting into the food web, into the water, and what can we do to change the geochemistry to be able to reduce that process of transfer. So you see a PhD student, Hilda, there working with a postdoc on a set of aquaria where we are studying these small systems in small aquaria. How do these chemicals go up in the fish? What kind of interventions we can do to reduce that uptake? Once we figure that out, we can build our models to transition that into looking at what will happen if I do it in a lake. So the lake becomes the aquaria now. And we did that through multiple studies. We demonstrated that we can actually make a change to bind up the pollutants strong enough that it doesn't go up into the food web with the right kinds of amendments into these sediments. And the picture you see here on the right here is one of the sites where they are actually using it at a commercial scale. This is being done by the Navy in Hawaii, where they're cleaning up a marina using one of our technologies. And the ultimate goal there is to be able to finally reduce that exposure, reduce the pathways of exposure into the food web so that the top levels of in the food web, the predators and human beings who end up eating the fish are not impacted by these chemicals. So it starts off with understanding the science right, being able to describe that science quantitatively using math, and then simulating types of interventions and engineering approaches that would be suitable to reduce that exposure to make it better, make the environment better and make it more livable. So with that, I will end my talk. Thank you.